Another sound that could work would be kind of a dripping water sound, but that requires a very loose cheek to pull it off. And if there's any hint of smiling, at least with my face, I can't do it.
I'm trying, but it's so quiet.
I just am not good enough an actor to tell myself to stop smiling. This is too much fun.
That was Alan Schaefer, an organic chemist at East Stroudsburg University in Pennsylvania. And I'm Tian Nguyen, here with Carrie Jansen for Stereochemistry.
Hey Tian, quick question. Why were you two talking about mouth sounds?
We were talking about the sounds reactions make. Well, not the literal sounds, the clinking of a stir bar or the hum of a rotobap. He was talking about what noise a reaction mechanism would make if it could make one. The water drip sound is what he envisions it sounding like when a proton transfers from one reactant to another.
Ah.
You know, as chemistry reporters, it's our job to explain complex concepts in simple ways. So we totally understand Alan's desire to come up with sounds that might help students understand or remember chemical mechanisms. We encountered a few other situations this year where we were searching for ways to better explain some tough chemistry concepts.
As a way of wrapping up the year, we're going to look back at some of those stories, and we're going to have a little fun while we're doing it. We'll try to describe some Nobel Prize-winning science, and we'll hear a song of defining or redefining the mole. But first, let's get back to Alan sounding off on chemical mechanisms. So, Tian, what possessed Alan to start trying to capture the essence of chemistry reactions with sounds?
Well, back in February, he saw a story about music appreciation and organic chemistry that appeared in CNN's Newscripts.
The weekly column covering the quirkier side of science.
Right. And in the story, Professor Ginger Schultz at the University of Michigan asked her students to come up with ways to connect chemistry with music. And the students totally went for it. They rapped about benzene and sang pop renditions about addition chemistry. Anyway, this Newscripts column got Alan thinking.
It was kind of a nice reminder of how valuable and fun it is to try to connect different disciplines together, looking for the common themes and ways that one discipline can inspire another discipline. So that got me to thinking of Victor Borge, one of my favorite performers, and how he was able to bring music and comedy together.
Borge Rosenbaum, known as Victor Borge, was a popular musician and comedian in the 40s and 50s. One of his most famous routines was phonetic punctuation. In the bit, he comes up with mouth sounds that describe punctuation marks.
A period sounds like this. An exclamation point is a straight line with a period underneath. Question mark is rather difficult.
And putting those mouth sounds in your sentences can really liven up your storytelling. Psst. Alan decided he wanted to try something similar to help reaction mechanisms come to life for students and make learning them a little more fun. Reaction mechanisms are basically the step-by-step description of the changes a molecule goes through in a reaction. Organic chemists call this arrow pushing because you draw arrows to show electrons pushing the reaction forward from A to B to C until you get to a final product. Students have to learn a ton of these mechanisms. Take the E2 elimination mechanism as an example. An E2 reaction is when a molecule's hydrogen atom gets ripped off and the electrons that are left behind from that bond collapse onto the carbon that it was attached to, pushing off a nearby halide atom and ultimately creating a new carbon-carbon double bond.
Kind of a drastic change in structure, a lot of things happening at once, kind of a gutting of the molecule, so to speak. So that would kind of perhaps parallel Mr. Borge's question mark, phonetic punctuation, kind of the schlepping sound, just as one suggestion. But the more dramatic the change in molecular structure would, imply the appropriate, quote unquote, use of a more dramatic mouth sound. So SN2 and E2 would be logically more amenable to a more dramatic sound.
In an SN2 reaction, one molecule sort of sneaks up on another molecule, kicking off one of its atoms and taking its place. It's an attack from behind, really.
So an SN2 could be a kind of a cricking sound to imply the inversion of configuration.
That makes so much sense. Now consider a less dramatic reaction like an SN1. An SN1 is similar to an SN2 reaction, but instead of an atom being pushed off the molecule by some usurper, it leaves on its own.
Like, take my place, whatever, I don't care.
Right. So in an SN1 reaction, an atom still leaves. It's just a gentler goodbye.
It could be kind of like a sound that parallels a tennis racket hitting a tennis ball in an indoor court.
Alan had lots of other creative ideas. For rearrangement reactions, basically atoms playing musical chairs within a molecule.
That could be maybe a whistle sound, something like that, because it's so easy. Essentially no activation energy barrier for that process.
For electrophilic aromatic substitution reactions, which are driven by an aromatic compound's electrons, Schaefer says those can be thought of as sort of a cloud of electrons.
So that could be more like a sound,
Yeah, and you always have to remember with electrophilic aromatic substitution, you have to remember the rules of whether or not it's electron-rich or electron-poor to know where on the ring it'll go.
So you could vary the volume of the shush sound, I guess, if it's activated or deactivated, right?
Yeah. Or maybe an inhale or an exhale.
There you go, yeah.
Alan says his students' response to his reaction sounds comedy varies from class to class, but he doesn't mind taking that chance if it might help simplify complicated chemistry.
We were challenged with another complicated subject earlier this year when CNE uncovered the 2018 Nobel Prize in Chemistry.
The prize was announced at 11:45 a.m. in Sweden, which is 5:45 a.m. for us in DC, and 2:45 a.m. for our poor news editor Michael Torres on the West Coast.
Oh, that was an early morning. We did get breakfast sandwiches, though.
And they were delicious. So before the sun was even up, we were in the office, huddled around a laptop listening to the announcement, which, for posterity, we recorded. In case you don't speak Swedish, the prize went to Francis Arnold, George Smith, and Gregory Winter, whose work was all related to harnessing evolution to identify new enzymes and binding proteins. And we were all clearly very excited about the winners.
Before the announcement had even finished, CNN reporters were scrambling to put together a succinct explanation of the prize-winning science. One piece of that puzzle was phage display, developed by George Smith of the University of Missouri. Phage display is a library-based method that screens for proteins that bind a specific molecule. And to be honest, I still don't really know what that means. So when we heard George Smith would be just a few blocks from our offices in Washington, D.C. with other Nobel laureates for a symposium at the Swedish Embassy, I thought, why not get an explanation of phage display straight from the inventor himself? He graciously agreed to talk with me for a few minutes, despite being a bit hoarse from a cold. We're a chemistry magazine, and we even had a hard time wrapping our heads around phage display. I'm curious, do you have a one-sentence or two-sentence explanation that you pull out sometimes when you need to?
Well, my son had a one-sentence explanation that he put on Twitter, and he said, my dad got the Nobel Prize for putting the red thingy in the blue thingy so that it could grab onto the yellow thingy. Does that help? I don't know if I can do it in one sentence.
The tweet played off a colorful graphic tweeted by the Nobel Foundation announcing George Smith's winning work. The red thingy George's son was talking about was a gene coding for a particular molecule, a peptide, let's say. When you insert that gene into a phage, the phage synthesizes the peptide and then plants the molecule on its surface on top of the blue thingy, a protein in its outer coating. The peptide sits out there hanging around until a molecule it recognizes, the yellow thingy, an antibody, maybe floats by. Then the blue peptide snags it. It's basically a molecular capture system that's been given strict DNA blueprint instructions on how to operate. I asked George if he remembered the first moment he thought he might be onto something in his work with phages. He called back to early work done by his postdoc Jamie Scott, creating a huge library of phages, each with a different protein attached. Jamie then used a known antibody to pluck out phages with the specific protein that would bind to that antibody.
So that was the first time that we managed to select out of a huge library very rare structures that had the expected structure. We also had some unexpected ones. So that led us to realize that you could discover new things this way that you wouldn't anticipate by the knowledge you have. I call this kind of engineering, you might say, ignorance-based discovery, because you're not requiring great specific knowledge about what you want. You use your knowledge to create a system to select what you want, rather than being able to design it in advance.
You can learn more about this year's Nobel-winning research on our website. We'll post some of those links in this episode's description. And don't miss Bethany Halford's profile of chemical engineer Francis Arnold, whose work with directed evolution landed her one half of the chemistry prize.
So we've now heard about 2 different ways to simplify complex subjects, using mouth sounds and color-coded tweets. But wait, there's more.
We're going to take a break, and when we come back, we'll hear from a minstrel of chemistry about another creative approach to breaking down complicated ideas.
Hello, Alex Taylor here from the production side of CNEN. It's that special time of year again when CNEN staff reminisce about the year's most memorable chemistry. To celebrate, we put a special collection of stories together highlighting science that stood out in 2018. In the research realm, we take a look at major trends, including the rise in machine learning, gains in treating hearing loss, and polymer science solutions to our plastics problem. Our editors share some of the science that made them smile in 2018. And don't forget to check out a crowd favorite, the roundup of our molecules of the year. Readers voted on which one they thought was a cut above the rest. You don't want to miss it. You can find all of these stories and more at cenm.ag/YIC 2018. We'll put a link in the description. Now back to the show.
A mole is an animal that burrows in the ground, or a spot on your chin that you gotta shave around. But there's another kind of mole of interest to me. That's the kind of mole they use in chemistry.
That voice you just heard has echoed in my mind since high school chemistry, when my teacher played this song to introduce a lesson on the mole, the unit chemists use to define an amount of atoms or molecules. And more than 10 years later, I still remember the upbeat chorus.
A mole is a unit, or have you heard, containing 6 times 10 to the 23rd. That's a 6 with 23 zeros at the end. Much too big a number to comprehend.
That catchy tune came to mind again this past fall, amid news that the mole was being redefined.
Officially redefined, though in practice, most people probably won't notice a difference.
Here's the deal. Since 1971, the mole has officially been defined in relation to the kilogram. A mole is the amount of substance that contains as many chemical units as there are atoms in 0.012 kilograms of carbon-12. The kilogram is actually a physical object, a platinum iridium cylinder that's kept under tight security in the International Bureau of Weights and Measures near Paris. The measurement of that cylinder defined the kilogram, which was then used to define the mole.
But in November, scientists from around the world voted unanimously to redefine the kilogram and the mole.
Starting on May 20th, 2019, each of those units will be defined by a fundamental constant that's been measured precisely by various instruments. For the kilogram, that constant is Planck's constant. For the mole, that constant is
Avogadro's number, approximately 6.02 times 10 to the 23rd.
Right. So that means that the mole will be defined as an amount of entities equal to Avogadro's number, independent of the kilogram. In practice, the redefinition is not a major change, but the scientists involved say it will make measurements more accurate and stable. If that sounds complicated, I agree with you. The mole is a complicated concept, so I got to wondering about the creator of that ode to the mole that I remember from high school. Who was it that decided to take on defining the mole in song and created this tune that seemed to be permanently embedded in my brain?
6 times 10 to the 23rd,
So I did some digging. Versions of the song I found online are credited to a Mike Offit, who I learned is a retired high school chemistry teacher living in Illinois. It turns out he's created and performed dozens of science-themed songs about chemical reactions, physics, energy, atomic theory, and, of course, the mighty mole. And in late November, I caught him on the phone.
I mean, I gotta tell you, that was more than 10 years ago. And even to this day, when I need to remember what a mole is, your song pops into my head.
There you go.
Mike taught high school chemistry for 32 years, but his science songwriting actually started with a different area of science, physics. Back in the 80s, he says, one of his colleagues was teaching a lesson on reflection and refraction, which made Mike, a lifelong musician and songwriter, think of looking at the two sides of a spoon and seeing the reflected image change as you move the spoon closer or farther away. Mike thought music would be a powerful way to emphasize a particular topic.
So I got this crazy idea to write this song. It's a physics song called Amazing Spoons, and it's actually you play the spoons. I know how to play the spoons.
Spoons, spoons, amazing spoons. You can sip your soup, you can play a tune. And if you look real close, you can see a scientific mystery.
And so I did it for his class, and they loved it. You know, that got me hooked because I thought, well, my gosh, what a neat way to emphasize, an idea. And then I had to write chemistry songs. I had to do a mole song because, my gosh, that's a very big idea in chemistry. What made it fun was that I would try them out and see how they worked. And so I tested them out in the classroom, and then from there I put together these little albums and sent them off to a teacher publishing house company, and they published it, and then it started getting out there, and teachers started using it, and they began calling me up and asking me to come to their classrooms if it was local, and I became sort of a minstrel of chemistry there, and it's been a wonderful, wonderful experience over the years.
Altogether, Mike has 3 albums of chemistry songs and also an album of physics songs. Every year he writes a new song about the mole for the National Mole Day Foundation, based on an annual theme. He's been doing that for almost 30 years. I asked him how the songs come to him.
Well, that's the nice thing about when you write music that relates to what you're teaching, your program. Every time you get a new topic, there'll be something that you think is really important for your students to understand. And so that is a great idea for the topic for a song. Say you're going to teach redox. The big idea is oxidation is a loss of electrons, reduction is a gain, or just the number 6.02 times 10 to the 23rd. When you get into the definition of a mole, that's a hard number to remember. But if you have it in a song, like you remember how many years ago, it's just still like an earworm that's stuck in your brain. It'll pop out every now and then.
6 times 10 to the 23rd.
Yeah, it works. But wait a minute. Defining the mole as a constant, Avogadro's number, is the new definition. Why is it in a song that I remember from a decade ago? Well, as CNEN's Laura Howes reported in her story on the redefinition, most chemistry students already understand the mole as 6 times 10 to the 23rd particles, and teachers often use that definition too. So in that way, Mike's song was ahead of the game. I wanted to know if Mike knew of this shift in thought and what he thought about it.
So the other thing I wanted to ask you about, I'm curious, have you seen the news that the mole is actually being redefined now?
The mole? Oh. Now, wait a minute. Hang on just a second. Or do you mean the... Oh, okay. Don't you mean the kilogram?
Well, the kilogram and the mole.
Oh, I had no idea the mole was being redefined. That is fantastic.
I gave Mike a quick rundown of the redefinition news and how it turns out his song was sort of foreshadowing the scientific community's shift in thought.
I think your song might still be right. Your song might have been on the new definition the whole time.
There you go. That was a precursor to the modern way of thinking.
That's right.
Great.
Mike says he's grateful for the many students over the years who entertained his scientific serenades and for this unique chance to share the wonders of the science of chemistry.
I really feel satisfied and happy that something that I did for fun ended up being kind of a nice part of people's memories of their chemistry class. A lot of people now are coming up to me and said, I remember your song. And that really kind of feels good because it usually is in a positive way. They remember singing it as a group and smiling and laughing and just sort of feeling good.
So, Tien, I played A Mole as a Unit for you just a couple of days ago. How did it make you feel?
It made me feel great. And I don't know how this happened, but I had actually never heard it before.
And now it's stuck in your head forever.
Yep, forever. Thanks.
I want to say thanks to everyone who has supported stereochemistry with your listens and your clicks over this past year, our first year. Tune in next month when we'll kick off 2019 with a look at how and why some drug companies are going after RNA to fight disease. From all of us at Stereochemistry, have a happy new year.
And in honor of the historical significance of 2019, the International Year of the Periodic Table, we'll play you out with Mike's song on Mendeleev, who came up with the arrangement of the table that we know and love today.
Who told the elements where to go? Mendeleev, who put them in columns and in rows. Mendeleev, who was ready, who was able to make a periodic table. Who was that chemist? Mendeleev.